Assalamu alaikum everybody. Hello, Abdullah here, and I'm gonna be today we're gonna be talking about residues, complex analysis, and hey guys, so uh, residue. Now we might have heard. Now when we talk about why do we actually need a residue, remember might be a lot of definitions. The coefficient of the a to the negative term, or basically the coefficient of the negative x to the term of the Lorentz series, right? And you might be like the thing where the singularity is there. But first, we need to understand. In order to understand what a residue is, we need to understand a contra integral. Now look, contra integral usually it's something like a complex plane, right? We use complex numbers here, an imaginary axis and a real axis. Now this plane, every point on this plane, if we plot a function which is holomorphic, what is it? It's holomorphic. Holomorphic means like analytic, but in a better tone, I guess. But basically means differentiable at every point in C, like at every point in C. Now mesomorphic means, which means it is holomorphic except for at the singularity. So we're just talking about like functions that are mesomorphic. So let's say let's choose the simplest function out there. 1 by z, which has a singularity at z is 0, right? You might get what I mean. Like, so I can say z squared plus 5z plus 2z plus 2z minus 2, let's just say. So there are points at two singularities, right? So, or because it's complex, let's make it fancy and just say z squared plus 4. Z can be complex differentiable at, not be complex differentiable at 2i and minus 2i. Am I correct? Let me just. I mean, it looks correct to me, right? Something like z square. Yeah. So we're obviously, if you should know that I is the square root of -1. That's the like basis of how we represent complex numbers here. Like how we started with complex numbers, how we represent them. Complex numbers represented like something like this. And if you want to write it in exponent form, you can write it something like this. I'm pretty sure that's quite. You already know all this stuff. We're assuming you know complex numbers, you know the basics and everything. But when we're talking about there are two things when we consider them. One is zeros, and one are poles. I'll just tell you what I'm talking about poles here, because poles, residues are formed at the poles. So zeros we don't really like. Yes, like zeros they don't really produce those residues, as in, but poles are the special kind that produce residues. Now, what is it? How do we compute the residue? Is a pole the residue? Like I'm talking about this function right here. These are the singularities, points of singularity where the function blows up to infinity, blows up, bang bang. Like, think this is my complex plane. This is 2i. This is negative 2i. It blows up here. Okay, at this point, like you can show it by colors or 3D or whatever. It's not analytic here. So what we do in complex analysis is that we draw a little neighborhood, a deleted neighborhood, or you can say, a small circle of radius epsilon, where epsilon is obviously greater than 0, and but it's a very small number. It's like, you can say close to infinite. I don't know. Like you probably heard of if you've studied limits, you know it's like converging to a really small part where just to get the singularity, right? But we just show it like this so that we can actually show it, because if you make it any smaller, then that simply wouldn't that wouldn't be real appropriate, right? If I just make it like a dot there, something. But we just draw it like this so we know it's there. So we gotta complex integrate in this part where the singularity. Sometimes the the residue just as a procedure, like for these functions, but we're not going to talk about that. I'm going to talk about how to compute a residue. So the residue for a function at a point, the formula is quite simple. It's limit as z approaches z naught. Oh yeah, sorry. And z minus z naught and f of z. Again, z, don't put z as z naught in the beginning. Try to find, limit means you try to basically like you try to you know, like make the form a little easier to understand, or whatever you can say. So it's, if you put it in this case, it just becomes zero, but we're talking about a real function. So how about we actually do it for a real function? I want to complex integrate 1 over 1 plus 4x squared dx. How about I complex? So I use the complex variable z, complex integrated. So complex variable z and dz. Points of singularities. Well, here was 2i and minus 2i. I'm not using this example, okay? This is a different example. As you can see, that was z squared plus 4. So we're just gonna factor this 4 out. Where this turns 0, the denominator turns 0, function is undefined or blows up, okay? So we can say it's z, sorry, plus 4 here. Yeah, I'm really sorry about that. Plus 2i, sorry, half I. You just root that thing, right? Z minus half I is 4 goes to 0, just cancels off, right? So this part is just shows that z is undefined at half I and negative half I. Now, in order to choose which singularity to deal with, like it could be either only the positive ones, it could be I'm complex integrating on this part, or it could be below the x-axis. So which one do I choose? Right now we're gonna choose the positive, but there is an intuition behind it, which I'm going to explain to you in this video. So yeah, the intuition behind is like, if I multiply anything by e to the ix, like I just multiply this thing with e to the ix, this actually is 1, it's an absolute value of 1, and we're you gotta take it in your head that we're actually talking about an imaginary number in the real world. So the only way that's possible is if we take the complex plane one turn and it's on the real value and it's on 1. Well, you might say it could be a negative 1, right? We usually consider the modulus, like the unit circle, the radius here. That's what matters. Yeah, it's not like it's spinning around or something. So we can usually multiply this part, and we can basically say e to the ix is e to the I, because we're considering a complex variable. So we turn it into the complex world. We can take it as x minus e to the I hope that makes sense, dot e to the yeah, iy, sorry, x plus, sorry, oh yeah, what am I doing? So minus y, right? Does it make sense? E to the x, sorry, we don't have I here. E to the x minus y. Now we have to look at when we go, since that's the only way this exponent works. If you had a different sort of exponent, you know, different absolute values or blah 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 blah, different function. Yeah, so basically this part, we gotta look at what happens, the intuition behind. So if the imaginary direction, which is y, it goes up in the imaginary direction, like when we move up in the imaginary direction, greater y, that makes it decay. Greater y makes it decay. And if it's less than y, well, you sort of know what happens, right? Less than 0, sorry. Less than y is greater than 0, y is less than 0, then you can really see that e to the negative y will basically There is already a negative sign, and if y is also negative, see what's gonna happen here? It's gonna be positive and it's gonna blow up exponentially. That's why we do not consider the case where the imaginary is zero. So we just plot the contour here, and we're gonna, sorry guys, I by 2 and minus I by 2. So we're gonna just consider the upper direction here. I hope the intuition was understandable. All right, so sort of just integrating the upper contour, upper, like the positive imaginary part. I hope that was clear. But then we're gonna look at how do we compute the residue. Now this was the formula for the residues, for how to compute the residue. This was the easier part. There's another a little harder one, but you can go check that as well. But this is the thing. So now, what was my function here? Okay, I hope you had this intuition clear, so I just want to erase this. So as a limit, it's okay, residue of the function 1 over 4, sorry, 1 over 1 plus 4z squared, comma, at z naught, at the essential singularity, because we're not considering minus o I by 2, we're just going to erase that, I over 2. Now limit as z approaches z naught would be z minus I by 2, and our function can already be factorized as z plus I by 2 and z minus I by 2. Now the intuition was hard, like the intuition was lengthy, you can say, not even hard. But now you see the major part, it really is just simple. Z is approaches z naught, which just basically means I by 2 plus I by 2, right? I hope that makes sense. I think I've made a mistake here. Yeah, 4. I forgot to take the 4 out here. See? Yeah. So now we get 1 by 4, and half plus half just equals 1. So 1 over 4i. And we should know that there's 1. Multiply that by I. This circle sort of made like a tetrahedral thing. Cycling. Okay, it multiply by that I, you get minus 1. Multiply by that I by, multiply that by I again, minus I, 1. And minus I is the same as 1 over I here, because 1 over I can just be written as I, let's just be I divided by minus 1, which is minus I. So we can write this as minus 1 by 4. No, the 1 by 4 will be the same, but the I is different. Golden, right? This is the residue. This is the residue. But when me computing the integral, across this part, we're basically considering this arc length as well. So we're gonna be taking it to be minus I by 4. Like, got your residue theorem, 2 pi I times sum of residues. So 2 pi I times minus 1 by 4i. Or you can just write it as, making it negative just makes it more like, actually it makes things less orthodox for us. So we can just cancel the i's here if we put it that way, and that makes it 2 pi by 2, a real positive answer. And in terms of pi, so that's beautiful, I guess. You can check this out yourself. There's another way to do it. It's something like n to the z over d to the z. It's represented as a rational function, and d to the z is should be 0. D to the z can't be 0, and d to the bar z should be 0. It's a little different way, and I would like if you will look out what this is. I'm not going to tell you exactly what this is, but you just, this is your this is an assignment for the viewer. Okay, thanks guys. I hope this was informative. Well, there's a lot of things about complex analysis. So I mean, I was very, I know I was brief, and I was like I was very you might not have understood a lot of things if you don't know basic complex numbers or stuff like that, and I didn't make course of that. So my apologies if you find it inconvenient, but thank you guys. Bye.